benchmark. By seeing these numbers, you can say, oh, that's bad. But you're seeing it at a wrong perspective, because this shows to us that there's a lot of room for improvement. And so that's a lot of fun for us. And so I didn't investigate a lot for this benchmark, but my guess is that garbage collection and synchronization here are really making VMKit really have bad performance. For .NET, we compared with the two other virtual machines, two other implementation of the common language infrastructure, which are Mono and PNet. We didn't compare to Microsoft because, well, first of all, Microsoft doesn't allow us to do that. And second of all, the .NET implementation of Microsoft only runs on Windows, whereas we run on Linux. So that wouldn't be fair. We use the PNet benchmark, which benchmarks scientific applications. And so here it's really impressive because we have really good performance compared to Mono, which has a large developed base and is here for ages. So on the SOAR benchmark, it's the same as on the JVM benchmark. The array bound checks are not removed. So why do VMKit shows that LLVM is losing its VM companion? So first, I wanted to show compilation time of applications. So in the previous slides, it's only performance. I didn't show you compilation time, okay? So VMKit uses a compilation-only approach, so there's no mixed mode execution, no interpretation. It's only, I have this function, I apply all these optimizations, and that's it. I have the code. So no interpretation. There's no dynamic optimization or on-stack replacement. So how does that affect application startup? Well, so we launched Tomcat, which is basically a web server written in Java with OpenJDK, the standard implementation of Java. And Tomcat boots in 3 seconds approximately. For VMKit, you can see these numbers, 40 seconds. So, okay, we apply a lot of optimization, so that's probably why we're having so bad numbers. But actually, if you launch VMKit without optimizations, you get 10 seconds less. So, what's going on? Is Evan here? Okay. When I came in the LLVM community and there was a bug, everyone told me, blame Evan. And so here it's true. I have to blame Evan, apparently. So LLVM, you can time optimization pass and code generation passes. And so that's what I did with VMKit running Tomcat. And you can see that with optimizations, a lot of time is spent in the x86 DAG-to-DAG instruction selection. Dan too? Okay. So Dan and Evan, well, Evan was there before Dan, so. Yeah, the optimization passes are taking some time, but not that much in the end. In the case of executing VMKit without optimizations, it's even worse. You get 24 seconds of 86 DAG-to-DAG instruction selection. So I don't want to know what's going on here. I just. Could you repeat it? No. But, well, we're a friendly community, so I could do that. Oh, okay. So I have to move there for the camera. Okay, so I don't want to know what's going on in here. Just event, please. One other missing feature in LLVM is that you cannot do parallel compilation, and that's for multi-threaded applications. That's bad because when a thread wants to compile a function, it takes a big lock, and the other threads who may want to compile a function to have to wait for that lock. So, and since compiling takes a lot of time, that's not good. So there's one big lock for cheating. So that means transforming your JVM bytecode to LLVM IR, generating LLVM types, applying optimization passes, and code generation. So that takes a lot of time, and that's really bad for multi-thread applications. There's also a set of missing features. I won't go into details for most of them. For the non-calls exceptions, so when you have field accesses or virtual calls on an object, so currently in LLVM, you need to do runtime checks to see if the object's not null. So you insert these runtime checks. This complexifies the control flow, gives a lot of pain to the optimization passes, and that's bad. So hopefully Nick is working on this. So we'll have non-calls exception support soon. With divide by 0, it's the same. You do a runtime check when you divide something if it's 0, and that complexifies the control flow. There's also arithmetic overflow. So in .NET, you have bytecodes which raise an exception if there's an arithmetic overflow. There's no such thing in LLVM, so you do runtime checks and you complexify the control flow. That's bad too. You cannot do bytecode checking. So when you go to JVM to LLVM IR, you lose the high-level types. So on the LLVM IR, you cannot do bytecode checking on type safety. You have to do that on the JVM bytecode. And since I'm lazy, I don't want to do that. There's also the type-based alias analysis. So since LLVM is losing all the type information, it cannot do a type-based alias analysis, which would really help because it would say that two objects, one alias, and it could do optimizations on it and stuff. But well, so that's the missing features currently, which it shouldn't be too bad for performance, but it would be great to have them.